Even though it may seem that science has reached the level where there are no more mysteries left, it's not exactly true. And no modern physicist would dare to assume that our knowledge of the universe is near completion. What are scientists still wondering about? Let's figure it out. For one thing, dark energy keeps puzzling researchers even today, because the universe doesn't seem to add up. Even though gravity is pulling space-time, the very fabric of the cosmos, inward, the universe keeps expanding outward, and this process is speeding up. That's how the concept of dark matter was born. It's believed to be some invisible agent that counteracts gravity by pushing space-time apart. It goes like this. The universe expands, and more space appears out there, and with it, more dark energy. According to astronomers, this invisible energy must make up more than 70% of the universe. But no one knows how or where to look for it. Then there's dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Scientists call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. Its existence is inferred from the effects it has on visible matter, radiation, and the very structure of the universe. There are a few special detectors on the lookout for weakly interacting massive particles, of which dark matter might be composed. But so far, nothing has been found. One of the most recent studies claims that dark matter might produce long, fine-grained streams radiating out from Earth like hairs and streaming throughout the universe. But it hasn't been proven yet. Then, there's the question of antimatter. It's the oppositely charged and oppositely spinning twin of good old matter. The intrigue here is why there is more matter than antimatter in our universe. It would be logical to assume that the universe would want to treat matter and antimatter equally. Thus, at the moment of the Big Bang, equal amounts of matter and antimatter should have been produced, right? Not really. If it had happened, there would have been a moment of total annihilation. Protons would have canceled antiprotons, electrons, anti-electrons, and so on. It would leave behind a lifeless, matterless expanse of space. Luckily, for some mysterious reason, when the universe was created, there was some excess matter. It didn't get annihilated. And that's how everything started. But there's still no accepted explanation for this. Then, we've got particle physics questions. They account for many unsolved problems. Sonoluminescence is one of them. Let me explain. Let's say you take some water and hit it with sound waves. It forms bubbles, low-pressure regions surrounded by high pressure. Once the outer pressure pushes on the lower pressure air, the bubbles collapse. But while collapsing, they emit light, even though the flashes don't last for more than a trillionth of a second. What bothers scientists is that it's unclear what the source of this light is. There are a few theories, of course. Some experts think tiny nuclear fusion reactions might be involved in the process. Others believe some kind of electrical discharge comes into play here. There's also the idea of compression heating of the gases inside the bubbles. None of these theories have been accepted yet. This might sound surprising, but we haven't figured out what exactly gravity is either. Other forces are mediated by particles, but not gravity. Some physical theories claim that it might be carried by a hypothetical massless particle called a graviton. But no one has seen these gravitons yet. We don't even know what kind of detector can be built to spot them. Even if gravitons come into contact with matter, and we aren't sure about it, they do it extremely rarely. There's also a theory that gravitons are closed loops of energy, but again, it's just a theory so far. There are tons of other unanswered questions bothering our minds. What happens inside a black hole? Is string theory correct? What is the fate of our universe? Do we live in a false vacuum? Hopefully one day we'll find the answers to all these mysteries.
Imagine a basketball spinning on someone's finger. A point near the middle of the ball takes longer to spin back to where it started than the spot where your finger is. Earth spins in much the same way. People in the center of Africa are turning at 1,000 miles per hour as the planet rotates, while anyone at the South Pole doesn't really move at all, other than rotating in place. At the same time, we're all moving forward through space equally fast, since the planet is also hurtling around the sun at 67,000 miles per hour. The temperature at the boundary of our planet's inner and outer core is 10,800 degrees Fahrenheit. That's as hot as the surface of the sun. And the pressure there is 3.3 million times the atmospheric pressure at sea level. 2 or 3 years ago, an asteroid was pulled into Earth's orbit and started to travel around the planet. Even though it's no larger than an average car, it's still a big deal. Out of more than 1 million asteroids astronomers know about, it's only the second one to orbit our planet. Called 2020 CD3, it's our temporary mini-moon. It won't be with Earth for long, though. The asteroid is following a random orbit and is slowly drifting away. Temporarily captured objects, such as 2020 CD3, are rare. They need to have a specific direction and speed to be caught by Earth's gravitational pull. Otherwise, they either crash into the planet or fly in another direction. The movement of galaxies and clusters billions of light years away from us suggests there's some enormously massive body outside the visible universe. After billions of years, the expansion of the universe will make the space so sparse that we won't be able to see the stars in the sky at all. The moon isn't a perfect sphere. It's shaped like an egg. Plus, the satellite's center of mass is a bit more than a mile off its geometric center. Even though Venus is the hottest planet in our solar system, it still has snow. But not what you'd expect. It snows metals and rains acid. Not a great vacation spot. Saturn is mostly composed of hydrogen and helium, with some traces of methane, ammonia, and water. But it contains more sulfur than Jupiter, which gives the planet a smog-like orange hue. On Earth, sound waves make air molecules vibrate, which is why we're able to hear sound. Other planets and moons allow sound to travel through mediums like their atmospheres and oceans too. In space, though, it's said that there is no sound, since there aren't any molecules to vibrate and deliver sound waves. However, not all researchers agree on this, given that space isn't just a desolate vacuum. In between the emptiness, there are clouds of gas and other stray particles. So, depending on where you are, sound waves can be possible. Astronomers know for sure that the universe is growing bigger, and the speed at which it's ballooning is increasing all the time. But if the whole thing is swelling into something bigger, then it must have some kind of an edge, right? It's unlikely that people will ever find out, but if so, then what would it be? A ginormous brick wall and then nothing? An abyss that leads to nowhere? The most common theory is that the universe is shaped in such a way that it can't have an edge, but it's not the only idea. Another theory is even more difficult to comprehend. The universe is, indeed, infinite, and our part of it isn't that unique. It means that somewhere out there, there's another you, or rather, other you. One of them is just a bit shorter, another wears their hair in a different way, and the third one is identical to you in all possible ways. There's also a theory about a multi-universe that consists of many smaller universes, and the universe we live in is just a tiny bubble among other similar bubbles. Those scientists who support this idea are also sure that bubble universes can come into contact with one another. Then gravity starts to flow between them, and when 2 or 3 universes connect, a big bang occurs, just like the one that created our home universe. Neptune is the windiest place in the solar system. Clouds of frozen methane are whipped across the planet at a speed of 1,200 miles per hour. Neptune's core is solid and consists mostly of iron and some other metals. Its mass is 1.2 times bigger than that of Earth. The temperature inside reaches 9,000 degrees Fahrenheit. Astronomers also believe that at a depth of 4,500 miles, there might be a diamond layer where it's raining diamond crystals. On Earth, people are used to a beautiful sunset that's painted in hues of orange, red, and yellow. On Mars, however, the normally pinkish red sky turns blue as the sun goes down under the horizon. It's because Mars is much farther away from the sun than Earth, making the sunlight less intense. The fine dust in the Martian atmosphere absorbs the blue light and gets rid of the warmer colors that you typically see on Earth. Whether it's blue or yellow, both sunsets look spectacular. At around a quarter of the size of Earth, the Moon is pretty enormous relative to other satellites out in space. There's nothing quite like this situation anywhere else in the solar system. Pluto has a moon that's almost half as big as itself, but it's more like a twin than a satellite. There are more than 150 moons in our solar system, and Earth's is the 5th largest out of the whole lot. There might be a labyrinth of lava tubes on the moon. Not long ago, astronomers received the results of an underground lunar topography. They discovered a massive cave under the satellite's surface. About 30 miles long and 60 miles wide, the cave's likely to be the result of 3-billion-year-old volcanic activity. After streams of lava hardened, they created a thick, hard crust on the outside. But inside, lava kept flowing, melting the rock and forming tunnels and caves. Countless pits in the moon's surface discovered by NASA might be the openings to lava tubes. We can't dig up most of Earth's gold. 99% of it ended up in the center of the planet several billion years ago, attracted by the iron in Earth's core. We're talking about 1.6 quadrillion tons of gold here. That's enough to coat the entire planet's surface in 1.5 feet of the stuff. And if all those meteorites hadn't later smashed into the ground, bringing extra amounts of gold, it would be even rarer. Not so long ago, astronomers discovered a massive blob of some mysterious substance. It was hidden underneath the surface of the moon's far side. Its mass was the same as that of a pile of metal 5 times larger than the big island of Hawaii. The enigmatic something lies almost 200 miles beneath an enormous crater that appeared on the lunar surface billions of years ago. The blob likely has something to do with a super collision. It might be the metal core of the object that hit the moon back then. Scientists can't wait to lay their hands on the discovery. It could explain lots of things about the South Pole Aitken crater, the largest known in the solar system. If it was on Earth, its oval-shaped basin would stretch from Washington, D.C. to Texas. In 2011, astronomers discovered an enormous water reservoir simply floating in space around a supermassive black hole called a quasar. Floating water vapors have been found throughout the universe, but they aren't that common. This particular reservoir holds around 140 trillion times the amount of water in the Earth's oceans. It's one of the oldest, largest, and, at more than 12 billion light-years away, one of the farthest things known to humankind. Astronauts in space can lose about 1% of their muscle mass each month. To prevent this, they have to stick to an exercise regimen that lasts 2 hours every single day. The Milky Way galaxy and the Andromeda galaxy are going to meet in 3.75 billion years. They're moving toward each other at a breakneck speed. When the two galaxies collide, they'll form a huge elliptical galaxy. I won't be around then. Have you ever looked up at the night sky and tried to count all the stars? Yeah, good luck. Our galaxy, the Milky Way, has about 100 billion stars, but other estimates put it at over 200 billion, since calculating the exact amount is an almost impossible task, even for astronomers. As for the entire universe, there are at least 1 billion trillion stars. That's one with 21 zeros after it. For comparison, that means there are more stars in space than there are grains of sand on all of the Earth's beaches. Today, there are at least 4 pressing mysteries that physics still needs to solve. Humans have always wanted to fly, but it's always seemed impossible. The ancient Greeks told the myth of Daedalus and his son Icarus, who constructed wings of feathers and wax and flew away from the tower in which they were imprisoned. But that was just a myth. Around 1500 CE, Leonardo da Vinci constructed several contraptions made of wood in which he hoped humans could fly, but they didn't work. Obviously, there was a physics problem that needed solving. It wasn't until Dutch mathematician Daniel Bernoulli, some 200 years after Leonardo, solved the problem of how a wing should work. The Bernoulli principle of air pressure difference between the curved top of the wing and the straight bottom of the wing. So now, humans first possessed the knowledge of how to fly. But it still took almost another 200 years after Bernoulli for the Wright brothers to actually construct the first motorized airplane in 1903. Before we can travel to the stars, we need to solve some mind-boggling physics problems. As things stand now, We certainly can't accomplish interstellar travel by going in rocket ships propelled by chemical combustion. There are two reasons why it's just as crazy to try to fly to the stars by rocket ship as it is to try to swim across the Pacific Ocean. First, the stars are too far away, and second, our rockets are too slow. Even light speed is too slow. It takes light about 4 years just to get to the star closest to the sun. It would take a modern rocket ship tens of thousands of years to reach Alpha and/or Beta Centauri. Forget about it. Obviously, science has several challenging physics problems that still need to be solved before we'll ever be able to travel to the stars. But it can be done. First, the mystery of space itself must be solved. The question, what is space, is presently the biggest mystery in physics. Well, it seems like a very basic question, but even simple questions are very important, like, what's for dinner? Ugh, not meatloaf again. Some progress has been made in the last 100 years to find out what space really is. Albert Einstein showed us, with his theory of special relativity in 1905, that space is not just space, it's also time. Einstein showed that space and time are one thing. You are here now, and I am here now, in a relatively different space-time. It was the Lithuanian-German mathematician Hermann Minkowski, Einstein's math professor in Zurich, Switzerland, who coined the famous term, the space-time continuum. So now, we don't just have space anymore. Space is gone. What we have instead is space-time. The two are bonded into a continuum. Space and time are now a four-dimensional entity, sometimes called Minkowski space, which can be represented geometrically as a light cone. So let the here and now in the center of the light cone be the Milky Way. The past is the only part that we can see. We only see things as they were when they sent us the light that we can see coming from them. But as we move forward into the future, our horizon of light expands, and we can see more. So what is over here outside the light cone? We don't know, but there could be lots of things. We're just starting to get our foot in the door, but we're going to pry it open someday. 10 years after he published his special theory of relativity, Einstein published his general theory of relativity, in which he showed that space-time becomes warped in the presence of gravity. This became the next step forward. Suddenly, gravity as a force was gone. Now we have the gravity field, and it warps in the presence of mass. If space-time can warp in the presence of gravitational mass, can space-time break? And if space-time can break or rupture, what's on the other side? With these questions, black holes suddenly became the second mind-boggling problem for physics to solve. The study of black holes, a term coined by John Wheeler in 1967, a former co-worker of Einstein in Princeton, New Jersey's Institute for Advanced Study, became a preoccupation for modern physicists because black holes appear to rupture space-time and open up a fifth dimension. And if there are 5 dimensions, there could be more. Black holes are found in nature at galactic centers, where orbiting gas and light are accelerated by gravity to speeds beyond the speed of light. Since nothing can travel beyond the speed of light in this universe, could black holes lead to other universes? Fortunately, we don't have to go to the center of the Milky Way to study black holes. We can make them in a laboratory, right here on Earth. And what a laboratory it is! The Large Hadron Collider, LHC, in Europe, is a circular 16.7-mile-long underground laboratory designed to explore subatomic spacetime and the particles that inhabit it. The LHC is the largest machine ever constructed. So what does the Large Hadron Collider do? It smashes things, like protons and other particles that can be accelerated by the miles of underground electromagnets. After powerfully accelerating them to nearly the speed of light, these particles collide into heavy atomic nuclei, like gold for example. The bombarded nuclei then shatter into a multiplicity of smaller fundamental particles that protons and neutrons are made of. quarks of all kinds, colors, and flavors. And no, there aren't any chocolate-flavored quarks. Quantum physics is the study of matter and energy at these most fundamental levels. Now, with the Large Hadron Collider undergoing an upgrade, which will make it even more powerful, black holes will be able to be observed forming during these quantum-level collisions. These black holes will be teeny tiny, itsy-bitsy, quantum-sized. They're only expected to exist for a fraction of a second before dissipating. Scientists at CERN in Switzerland assure us that the black holes that they make will not fall through the floor and go to the center of the Earth and begin swallowing the planet. And that's a very good thing to know. The upgrade to the Large Hadron Collider will be completed between 2025 and 2027. It's part of our need to find out what space-time is, or else we might just be stuck on this little planet Earth without ever being able to explore the universe. Time is part of the mystery of space too. After all, it is called space-time. The mystery of time has been difficult to crack. However, exciting progress has been and is being made. Once upon a time, as the story goes, Albert Einstein was giving a lecture about the speed of light. In his famous formula, E=mc², the letter C stands for constant, because the speed of light is a universal constant of space. A student raised his hand and asked Einstein, "But doesn't light go slower through a glass of water?" Instantly, Einstein realized he had always focused his attention on how fast light goes, and never seriously considered how slow light can go. Together with his colleague, mathematician Satyendra Bose, they calculated in the early 1920s how dense of a translucent material it would take to stop light. The material became known as the Einstein-Bose condensate, but no one believed it could ever be created in a laboratory, until it was done in the 1990s. Dr. Lena Vestigard Howe of Harvard University created an Einstein-Bose condensate by supercooling atoms of sodium gas down to 1/1000th of 1 degree above absolute zero. That's the coldest anything can get. It's even colder than my bedroom during the winter. At this temperature, the atoms of the sodium cloud bond together and begin acting as one big atom. Space-time in an Einstein-Bose condensate takes on a completely new form that no one has ever seen before. Finally, by the use of quantum-sized technology, science was getting its hands on the fundamental structure of space-time. Inside the EBC, light stopped, time stopped, and physical atoms were able to be teleported instantly to other locations. All of these breakthroughs are only in the laboratory stage of development, which leads to the next problem physics must solve in order to bring these theoretical and technical advances out of the laboratory and into the real world of our social and political lives. That problem is energy. At present, civilization doesn't have a powerful enough, safe enough, or convenient enough source of energy to realize the construction, manufacture, and distribution of the advanced quantum technology that's required to do all the amazing things that we see now are entirely possible, including interstellar travel. But nature has the energy we need: stars. The force that binds the nucleus of atoms together is called the strong force. It's the mother lode of energy in the universe. Stars release this energy when, by their immense internal gravity, they implode hydrogen atoms. This is called nuclear fusion. Modern civilization doesn't have a nuclear fusion reactor that can do that yet. We, of course, do have the H-bomb, which releases the strong force from the implosion of atomic nuclei. But the H-bomb is not a particularly convenient source of energy to use, is it? Developed countries have many nuclear reactors that produce electricity from the strong force by breaking apart the nucleus of the large unstable atoms of radioactive plutonium. These are atomic fission reactors, and they have proven to be, well, not safe. Nuclear fission reactors must be phased out of operation as soon as possible. The race to build a working nuclear fusion reactor faces many technical and economic obstacles. The ITER reactor, presently being constructed in southern France, is an international project that uses the Russian tokamak design of a giant donut-shaped deuterium plasma. A consortium of 35 countries is involved in the ITER project, and they've already been at work on it for 35 years. Some 30 other fusion reactor projects, with various designs, are also under construction in several countries, with none of them yet achieving either a sustained reaction or net energy output. How long can the world hold its breath waiting for fusion energy? Now that's what I call a burning question.